Okay, so this is video number 2 in our review for the AP exam. Derivatives. We should know all of our derivative rules. Product rule, first times the derivative of the second plus the second times the derivative of the first. Quotient rule, the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. The derivative of e to the x is e to the x. The derivative of 2 to the x would be 2 to the x times ln of 2 times 1. And the derivative of ln is 1 over the inside stuff times the derivative of the inside stuff. And we do need to remember sine inverse, which is 1 over the square root of 1 minus the inside stuff squared times the derivative of the inside. And tangent inverse is 1 over 1 plus the inside stuff squared times the derivative of the inside. So with that in mind, let's do some quick review. So if y equals cosine 3x times sine 4x, y prime would be cosine 3x times this, which would be 4 cosine 4x, plus the second, which is sine 4x, times the first, which would be negative sine 4x times 4. And I think I had botched something up here. It's the first times the second, which I got, plus the second times the first. This should have been a 3x times 3. And no, you cannot do anything else with these because these are not the same arguments. So you can just leave it like that. Next is a common mistake. Y equals cosine squared of 2x plus 1. In this video here, in this example here, take the square to the outside. So then y prime would be drop the power down, repeat the inside, decrease it by 1, times it by the derivative of the inside, which would be negative sine of 2x plus 1 times the derivative of the inside yet, which is 2. Another problem. Y equals e to the 4x times the sine of pi x. That's going to be another product rule. So y prime would be equal to the first times the derivative of the second, which would be pi cosine pi x, plus the second, which is sine of pi x, times the derivative of the first, which is 4e to the 4x. Next, I think we would know something like this. Y equals e to the secant of 1 over x. Well, the derivative of e is the function itself, e to the secant of 1 over x, times the derivative of this, which is secant of 1 over x, times tangent of 1 over x, times the derivative of the inside stuff. Make this x to the negative first, drop the power down and make it negative 1 over x squared. So there would that derivative be. Next is what about function composition? The derivative, suppose y equals f of g of x squared plus 1, close it, close it. What would y prime be equal to? Remember in function composition, we start with the derivative of the outside. So it would be f prime. Repeat the inside. Times it by the derivative of the inside, which would be g prime. Repeat the inside, x squared plus 1 times 2x. And that is something you definitely see a lot of. Suppose we have y equals x times f of x cubed. So that would be another product rule. So it would be y prime is the first times the derivative of the second, which would be f prime of x cubed times 3x squared, plus the second, which would be f of x cubed times the derivative of the first, which is 1. I think we should be pretty good with that. Y equals, say, f of x times g of tangent x. Well, that would be a product rule again. So y prime would be equal to f of x times g prime of tangent x times secant squared x, plus the second, which is g of tangent x times the derivative of the first, which is what? F prime of x. Okay? There's that. Next is implicit differentiation. So every time we differentiate a y, we put dy dx, because we treat y as a differentiable function of x. It's just that they're not solved for y. So if I were to do the sine of xy equals y, what would that derivative be? Well, the derivative of sine is cosine. Repeat the inside and times it by the derivative of the inside. So the derivative of the inside would be the first times the derivative of the second, which would be dy dx, plus the second times the derivative of the first, which is 1, equals, and then the derivative of y is dy dx. This is the one students often make the mistake on, because this is a product rule, which requires a plus sign here, which requires these parentheses or brackets. So you need to put the brackets. Remember, in implicit differentiation, be careful of your parentheses and be careful of your minus sign if you have that in front of a quantity. That often gets missed. So you have no choice really here but to distribute. So you'll get x times cosine of xy dy dx plus y times the cosine of xy equals dy dx. Get all the dy dx's to one side. So dx cosine of xy dy dx minus dy dx equals negative y cosine of xy. So I'm going to take this over here and make it negative, take this over and make it negative. Factor out the dy dx, but be careful, because what's left here is a 1 when you take that out. So what we have left is x cosine of xy minus 1. And that does not simplify. If this was a monomial in the bottom, then we could take each of the tops and divide it by the bottom. But we cannot do better than that with it not being a monomial in the bottom. So again, make sure you follow your rules. If this was x over y, then make sure you're doing a quotient rule on that. And if you have ln's, the ln of something, remember the ln of a product is the sum of the ln's, and the ln of a quotient is the difference of the ln's. That helps to simplify things before taking a derivative sometimes. If we have something like e to the x plus y equals y, what would that derivative be? Something of the same nature, but not a product rule, would be the function itself times the derivative of the exponent, which would be just 1 plus dy dx equals dy dx. And then distribute, get the dy dx's to one side, and solve. Okay. Next, a very common question is to find the values of the variable so that f is continuous and differentiable. Very common question. So I want to find a and b so that f is continuous and differentiable. So, two key words requires two key parts. Continuity. Take the limit from the right and the left as x approaches pi. So if I put this in, I get the sine of pi equals, put that in, a pi plus b. And the sine of pi is 0, so 0 equals a pi plus b. Now I have to take the derivative part. The derivative of sine is cosine, and the derivative of this is a. So then the cosine of pi, put this in, equals a. Cosine of pi is -1. So a is -1. So then if a is -1, negative pi plus b, add pi, b comes out to be pi. So again, in handling this problem, you're asked again to find the values of a and b so that f is continuous and differentiable. Two parts. Continuity, take the limit from the right and the left of pi in this case, and then do the derivative part because you want the slopes to be equal from both the left and the right. So the slope for x less than pi is cosine x, and the slope towards the right, as we approach pi from the right side, is a. The derivative of this piece is a. And then you take the limits of each piece, pi into here is cosine pi, and this is just a constant now, which is a. And the cosine of pi is -1. Substitute this back in here and you get b to be pi. Okay? And next is finding tangent lines. Tangent lines mean we need a slope and a point. Remember, normal lines are the negative reciprocals. So if I have y equals x times the square root of 3 plus x squared, maybe at the point 1, 2, y prime would be the first times derivative of the second, which would be that, 1/2, make this to the 1/2 power. Drop the power down, repeat the inside stuff, decrease it by 1, times it by the derivative of the inside, plus the square root of 3 plus x squared times 1. So if x is 1 here in this case, this is just going to be 1 times 2, all over 2 times 1 squared is 1 plus 3 is 4. The square root of 4 is 2. So this is going to be 1/2 plus 1 squared is 1 plus that is 4, which is 2 times 1. So it's going to be 1/2 plus 2, which is 2.5 or 5/2. So my slope is 5/2. The slope of the line normal to that would be -2/5. And then if I have x being 1, put this back in here to get y, and y is 2. So my tangent line would be y minus 2 over x minus 1 equals 5/2. Cross multiply and solve. The normal line would be y minus 2 over x minus 1 equals -2/5. There's that. Just a couple more then. How about the inverse rule 11? Another important derivative rule we need to remember for inverses. Anytime that you are told that f at g at x equals x, or g at f at x equals x, that means f and g are inverses of each other. So if f of x equals the function 1 plus ln of x, then what would be g prime at 2? Well, by the rule 11, g prime at 2 equals 1 over, change it from g prime to f prime at g at 2. This inside stuff gets written from here without the prime symbol. So I set it up, g colon, f colon. This is 2, a 2 there, means a 2 here. I start inside. So then I'll set my function equal to 2. Subtract the 1. And I'll undo ln by base e both sides. And x would be equal to e. Or I can use my 83. Or you may have to take a stab at the 0 by guess and check. You try 1, -1, 2, -2. So this is an e, and this is e. So g at 2 is e. F prime is going to be 1 over x, is f prime. And then f prime at e is going to be 1 over e. But be careful, this is 1 over 1 over e. F prime equals 1 over x, and I put e in for x, I get 1 over e. And when I invert and multiply here, I get e. That's inverse rule 11. Okay, remember that if f equals 1 plus ln of x, in order to again find g prime at 2, the rule is 1 over f prime. This goes from g prime to f prime. Repeat this here without the prime symbol. And then we need g at 2, so you set a 2 here means a 2 here, because they're inverses, everything gets switched. Set the function equal to 2, subtract 1, AC both sides, x is e. And then f prime is 1 over x, replace x with e. But be careful here. F prime is 1 over e. And then when you invert and multiply, you just get that to be e. Okay, and next, just two quick derivatives here that we need to often remember are the sine inverse and tangent inverse. Suppose we want to find the derivative of y equals sine inverse of 3x over 4. So y prime would be equal to 1 over the square root of 1 minus the inside stuff squared times the derivative of the inside, which is 3/4. That answer is not acceptable. It's not cleaned up. So this would become the square root of 1 minus 9x squared over 16. Square that. Make this a 16 over 16. And then make this 16 minus 9x squared over 16. Take the square root of both the top and the bottom. And the square root of 16 is 4. But remember, we have to invert and multiply. This is all on the bottom of the fraction. So when you invert and multiply, you get this to become 4 over 16 minus 9x squared times 3/4. These drop out, and there's my answer. Let's do one with tangent inverse. The derivative of tangent inverse. Suppose we have y equals tangent inverse of e to the 2x. Y prime would be equal to 1 over 1 plus the inside stuff squared times the derivative of the inside, which would be 2e to the 2x. Power to a power means you multiply, so this would become 2e to the 2x over 1 plus e to the 4x. And there would be that derivative. So remember there that you do have to clean those up. And just one more on implicit differentiation. A very common problem is, suppose we have 3y squared minus x cubed minus xy squared equals 7. Okay, to find dy dx, this would be here 6y dy dx minus 3x squared. This is going to need a product rule. Be careful of the minus sign. So maybe the first I'll call as negative x and the second is y squared. So it would be negative x times the derivative of the second, which would be 2 dy dx, 2y dy dx, that is. So it's the first times the derivative of the second, which is 2y dy dx, plus the second, which is y squared, times the derivative of the first, which is negative 1, and the derivative of 7 is 0. So then, everything to dy dx is already over here. So then I'll have my dy dx, take this over and make it 3x squared plus the y squared. When that comes over, they become the opposite signs. And then I'll factor out the dy dx, and there it is. Okay? Remember, you're often going to be asked questions about where there's a vertical tangent. You set the denominator equal to 0, and as long enough it does not make both the top and the bottom 0, there's a vertical tangent there. Horizontal tangents occur where the top equals 0. Again, but make sure that that number or x and y's do not make the bottom 0. Horizontal tangents occur where only the top is 0, not the bottom. And what else is there? That's it. So just be careful here that when you take this by implicit differentiation, that you can pull out the minus and do your product rule. X times 2y dy dx plus y squared times 1, and then distribute the minus sign. But the biggest mistake there often is not distributing the minus. So that right there closes out our derivative rules. A brief review of implicit differentiation again. Finding the values of the variables so that f is continuous and differentiable. The inverse rule 11. So a good review of our derivatives. And just remember real quickly again that y equals, suppose we have the ln of e to the 2x plus 4 to the x squared. Well, that y prime would be 1 over the inside stuff times the derivative of the inside. And the derivative of e to the 2x is 2e to the 2x. Plus the derivative of 4 to the x squared is 4 to the x squared times ln of 4 times 2x. That would be y prime in that case. Okay?